Can you please let me know if you're able to see my screen?
Yeah, this screen is visible. Thank you.
Are you able to see the presentation now?
Yes, presentation is also visible. Just you can check whether it's moving to the next slide.
Is it moving to the
next
slide?
It's moving. Perfectly working. Yeah, thank you.
Thank you. Thank you very much, Kuntal. Hello, everyone. Good morning and welcome to the session. In the session, I'll give an overview on the application of deep learning to solve computer vision problems, such as object classification and object detection. This session is aimed for those that would like to get started with deep learning and hence covers the basic concepts in a very gentle way. I hope you find this session interesting and useful. Let's get started. So what is deep learning? Here are some common definitions that you can easily find. Deep learning is a type of machine learning or artificial intelligence method that imitates the way humans gain certain types of knowledge. One other popular definition is deep learning is a subset of machine learning where the system is inspired by the structure and function of the brain, and the system is called artificial neural networks. When you read through these definitions, one can understand deep learning as an approach to artificial intelligence that mimic human brain. Well, you can argue if artificial intelligence could match human intelligence or not, but we cannot deny that the large amount of data that's accumulated is an important factor that contributed to this growth in the deep learning domain or studies in deep learning techniques. Alongside these advancements, the advancements in the computing and storage system has further accelerated the growth in the deep learning domain. How much data are we talking about? A study suggests that by 2030, we will have around 572 zettabytes of data. What about the visual data like images and videos? It is said that on an average, 300 million photos are uploaded on Facebook and 95 million photos are uploaded on Instagram daily. With so much visual data, there is an increasing demand for visually aware recommendation and search systems. This is where deep learning and computer vision come together. Some of such systems that we are already aware of is the Google Images, which is an image-based search engine, and automatic photo tagging in Facebook that everyone would have experienced. Similar to this, there are a few more computer vision applications that use deep learning. Computer vision applications in military, especially on the targeting systems like guided missiles, they help in locating enemy aircraft, rocket, or missiles fired in their territory with increased accuracy and efficiency. Computer vision algorithms are used in surveillance and risk detection systems and also helps in gathering intelligence-related information. The other domain where computer vision finds application is the manufacturing industry. The manufacturing industries use computer vision for inspection purposes. Computer vision can detect structure anomalies and is more accurate than humans. Other important field where computer vision finds application is the medical imaging data. Computer vision allows us to make extensive use of medical imaging data to provide us better diagnosis, treatment, and prediction of disease. Computer vision basically exploits the texture, the shape, the contour, and prior knowledge along with the contextual information from the image sequence, and it provides in the 3D or 4D information that helps humans to better understand the image data. Many powerful tools are available. That includes image segmentation, pattern classification, tracking, reconstruction. These techniques are very much needed to bring the quantitative information or helps us to understand the quantitative information that is not easily available by trained human specialists. These technology and artificial intelligence slowly getting into our everyday lives. Like I said, data, enormous data is one that we get to handle. So it's easy for us to understand. We should know how to make proper use of this data so that it has significant impact when we develop solutions. Data labeling is one kind of data processing operation where it refers to the process of adding tags or labels to raw data such as images, videos, text, and audio. So why do we need to label data? Like I said, these tags form a representation of what information is present in the image data. If you label this data, you can in turn use this data to develop machine learning models. You can train the models to identify similar objects when it encounters an image or a video, a completely new image or a video that has object with properties similar to what it is trained to recognize. So with crowdsourcing platforms like Amazon Mechanical Turk, you can get the data labeled by anyone. However, given the amount of data that we are talking about, automated labeling speeds up the labeling process and also saves the human errors. One other important application and interesting application is the self-driving cars. Self-driving cars use computer vision to process visual data from a driving scenario, like the pedestrians, the road signs, and the road markings, and then determines the action to take, like should the vehicle be maneuvering or should it be braking. Few other domain where artificial is finding its way is smell and taste. Digital olfaction mimics the way how humans smell by capturing odor signatures. So they use biosensors. They capture the odor-related signatures and then use software solutions to analyze and display the odor data. Artificial intelligence interprets the signatures and classifies them based on a database of previously collected smells. So how does all this digital olfaction data turn into visible or valuable insights for the companies? Automatically, you can use this data, you can use this technology to automatically detect food spoilage in consumer appliances, reject or approve raw material supply, reduce R&D time for new foods and beverages, ensure fragrances of personal care products like deodorants and shampoos that last for a long time. And now that we have seen how much artificial intelligence is finding its way in mimicking what humans do, it would be a good point for us to start is by understanding what is human intelligence. Though the definition of human intelligence vary from one theorist to other, current conceptualization suggests that intelligence is the ability to learn from experience. You acquire information, you chew the information, and you use the knowledge, which is use the knowledge to perform any other tasks. So this is an important component of intelligence. The second ability is to recognize the problems. You learn something, you have the knowledge, then you put the knowledge to use. People must be able to identify possible problems in the environment that needs to be addressed. Once you recognize the problem, then you know how to solve the problem. People must then be able to take what they have learned to come up with a useful solution to a problem that they have noticed in the world around them. What is the important component here? Key component here? Learning. Fundamental requirement for learning is acquiring information. How do humans acquire information? Through senses. We learn about the environment through senses like sound that you're hearing, vision, what you see, sense of touch, what you touch, what you perceive when you touch an object, Through olfaction, there is a sense of smell, and gustation, the sense of taste. So the sensory perception involves detecting the stimuli, characterizing and recognizing it. What is the sensory interaction with the environment? So you have the sensory perceptual learning occurs only through sensory interaction with the environment and through practice and performing specific sensory tasks. It's more analogous to teaching a child to recognize objects in our day-to-day life. You show a set of objects to a child, it's very likely the child will not memorize or will not capture the characteristics of all the objects in the first time that you explain. But then when you keep doing it, they make mistakes, you correct them, you give them feedback, you give them inputs. So it's more of an iterative process. They keep learning until they get thorough. So the changes that take place in the sensory and the perceptual systems are a result of perceptual learning that occur at levels of behavior. Like I said, examples of perceptual learning include we developing an ability to distinguish between different odors, identify different types of music, or our ability to differentiate between different shades of colors. So simply, we can see human intelligence in this way. When there is a sensory stimulation, which means activation of one or more senses, the activation acts as the input data to the brain. The brain somehow processes the data and learns the underlying information. The more the human brain gets exposed to the data, the interpretation improves. In some cases, you can use the learned information to perform specific tasks. If the outcome of the task is good, we do nothing. We understand that we know how to interpret the input data in the right way. But what if the outcome of the task is not as per expectation? What we tend to do, we tend to analyze the information that we learned and see what can be improved. This is where the learnability aspect comes. So this process is called learning. Now our intention is to build a machine that mimics this entire human behavior. How do we do it? First, we will need to mimic the human senses. We are all aware that there is so much advance in sensor technology, and the sensors, we use sensors to acquire information by detecting the physical, chemical, or biological properties of any quantity and then convert them into readable signals. The signals can be of any dimension, say for example 1D in case of speech, 2D in case of images. This will be the input data that contain the information that we want, or that contain the information that our brain has to understand and process. Now, let us build a system, in this case, a computer or a software program, that mimic how human brain process sensory data. So how do we achieve this? This can be achieved by properly modeling the data and representing the data. This is where mathematical modeling and mathematical representation helps. You can then use this extracted information to perform a specific task or to conclude about something. If you are not satisfied with the task that we accomplished with the model or with the representation that we derived, then you can always come up with techniques or methods to improve your modeling or representation. When you do this iteratively, you're bringing learnability to your technology. This is where machine learning plays a major role. So when you see, this whole system is an artificial intelligence system. Now, I would replace the sensor with a vision sensor, which means I'm going to have a camera sensor. So what does camera sensor do? Camera sensor mimics the way how human sees. So the input data that I get from camera is an image. So I give this image to a computer. I get a good, I model the image, I get a good representation of the image, and then I learn the underlying information, or I say the features from the image that I can use to perform any desired task. This is called computer vision. So now, how different is computer vision and machine learning? So when you see computer vision technique makes use of image processing algorithms. So you capture an image, you process the image in a way that you can derive some meaningful information. The information need not be image itself, but it could be any data. For example, feature descriptors, which we will see in the coming slides. And then you humans, we decide what we do with the data. There is no learning involved. There is no learning in computer vision technology. So you just use it to perform something. Everything is hard coded. On the other hand, if you add a capability, say for example, you have image data, you modeled it, you learned the underlying information, you know you can use the image data to perform some X task, and then you're training your machine in such a way that an unknown data comes in, an unknown image data comes in. You train your machine to look into the data and check if it has the sample of the data that it's already been trained to recognize. When you bring in this learning capability, then the system becomes an artificial intelligence system. How do you bring in that capability? That capability we bring in through machine learning algorithms. So there are basically three categories of machine learning algorithm: supervised learning, unsupervised learning, and semi-supervised learning. What is supervised learning? So now let us think. You have a system. You have a set of known inputs, and you also know the desired output. So you tell your machine, this is the input you give, and this is the desired output. I want you to derive a representation that would map the given inputs to the right outputs. So when this information about the output is known, then it is known as supervised learning. What is unsupervised learning? In unsupervised learning, you have the set of inputs, but you clearly don't know the outputs. So you really don't give information to the machine about what sort of data is present in your input. Say, for example, you have an image which has several objects. Consider a book, a flower, and a bottle. In supervised learning, you clearly tell the machine, if your input values are of these XYZ nature, then it's a flower. If the input values are of ABC nature, then it's a book. In unsupervised learning, you don't provide the information. Rather, the machine itself tends to look at the features, look at the properties of the data that it has received, and it would try to do a grouping. Say, for example, your machine finds a yellow pixel. It tends to locate all the other yellow pixels surrounding the test pixel or the pixel under question, and it would say, oh, this pixel all looks similar and it is in the same neighborhood, so let me group this as one object. This is how machine learning or the system works in case of unsupervised learning. In semi-supervised learning, is you provide partial information about what the underlying data or what is the underlying structure that your machine learning algorithm should uncover. So now this is how you can see machine learning. So you have input data, you extract features. We haven't gone into what sort of features we are talking about. We will see that in the coming slides. So you extract features, and based on how the features, the distribution of the features, you assign them to a category. You basically perform classification. You tell this set of feature belong to this X object, the next set of feature belong to the Y object, and that's the output. You see here, everything is handcrafted. There is no learning involved. Well, this works for most of the applications, but there are always limitations. You will have to have certain assumptions about the data that you operate on, and this technique is more tedious and costly to develop. Hence, we have an alternative that uses neural networks. Deep learning is a type of machine learning. The only difference is, rather than a classifier or a clustering method, it uses neural networks. So you're given input, you don't teach the neural networks, or you don't have a separate feature extraction and classification step, but then the process of feature extraction and classification is completely left to the neural network itself. We will get into the detail of this neural network in the coming slides. So basically, this is the advantage that deep learning offers over the traditional machine learning algorithms. You don't need to separately look for features, derive handcrafted features. The features would be automatically derived and can also be, it's more learnable as well. That's why we see computer vision is part of artificial intelligence. So machine learning techniques is also a part of, it's a group within the artificial intelligence technology. Deep learning is just a subset of machine learning. So in this session, we'll just look at the deep learning concepts or deep learning techniques that finds application in computer vision technology. Okay, what is computer vision? See, there are images everywhere. What is computer vision? See, we basically would like to, like I said, a camera mimics human eyes. So the computer vision system that I develop would like to mimic the way how human visual system processes an image. So in 1959, Hubel and Wiesel experiments greatly expanded the scientific knowledge of sensory processing. So in an experiment done in 1959, they studied how the visual cortex of the mammals function. This is popularly known as the cat experiment. So they put a microelectrode into the visual cortex region of the cat, and then they projected patterns of light and dark on a screen in front of the cat. These electrodes, based on the stimuli in the cell where the electrode is inserted, the electrode will record patterns. They found that. Hello.
I think there was a noise, so I muted that participant. Sorry about that. Please go ahead.
Yeah, no problem. Thank you. So they found that some neurons fired rapidly when presented with lines at one angle, while others responded best at other angle. So it's like this. Suppose, say, human brain is composed of many cells that we call it as neurons. Suppose, say, this is one neuron, this is one neuron, this is one neuron in the cell. And this is the object that we see. Imagine a vertical bar. So imagine this as a paper where this background region is black and then this region is all white. Not all neurons will respond to this. Only certain neurons will respond to this pattern. Say, for example, the first neuron is able to respond to this pattern. The second neuron and the third neuron need not respond. Whereas I put up a different pattern, something like a diagonal line like this, then the second neuron might get excited, where the first neuron and the third neuron might not respond. So basically they tell this neurons not all neurons respond in a similar way to the stimuli. So they called these neurons as simple cells, whereas they also found that there are other neurons which they called as complex cells that detected edges regardless of where they were placed in the visual cortex of the brain and could preferentially detect motion in certain directions. So it says that your visual cortex is made up of the vision, how the visual system works is more in a hierarchy. You have simple cells that respond to light orientation, and then you have complex cells that respond to light, orientation, and movement. And there are hypercomplex cells that respond to movement, with an endpoint. So these studies showed how the visual system constructs complex representation of visual information from simple stimulus features. With this understanding, we will see about another major breakthrough in studying the human visual system. In 1970, David Marr, he proposed 3 different levels for understanding of information processing system. One of the important contribution in Marr's study was made on the level of representation and algorithms when he proposed a representational framework for the vision. He concentrated on the vision task of deriving shape information from the images. It is known that the intensities perceived by any visual system are a function of 4 main factors. First, the geometry, meaning the shape and its relative placement, the spatial position, and then the reflections of the visible surfaces, the illumination, and the viewpoint. So according to Marr, the early visual system derives representations in which these factors are separated. So it's basically the human visual system inside your brain. You can consider these things as the primal sketch things as the simple features that was explained in Hubel's experiment, and then the 2.5 dimension sketches as the second level, what complex cells perceives, and the third one could be what the hypercomplex cells perceive. When a cell tells through 2.5 dimension, it does not literally mean a physical half dimension. It's basically a perception. So when you look at a 2D image, technically it's a 2D image. The 2.5 dimensional sketch says that it's intended to essentially perform the separation between the primal sketch and the surface orientation, or the changes in the intensity. So the deduction of intensity changes on the surface of an object, the representation and the analysis of the local geometric structures, and the illumination effects takes place in the process of generation of the primal sketch. So one important principle of the primal sketch is that independent spatial organizations of the intensities viewed in a scene reflects the structure of the visible surfaces. And that is what correspond to low-level features, which we call it as edges, blobs, or corners, likewise. Whereas the 2.5 dimension sketch is intended to represent the orientation and depth of the visible surfaces as well as the discontinuities. So what do we mean by this? This 2.5D representation is completely viewer-centered. By its very nature, it is viewer-centered. We only actually see things as they relate to us. See, while the result is technically 2D, it allows you for the illusion of depth. The last representation of the Marr's framework is a 3D model representation. So this representation is intended to describe shapes and their organization using a modular and hierarchical organization of volumetric and surface primitives. With these basics, there were several image descriptors that were proposed in 1970s. One of the early descriptors or the geometry primitives, suppose consider image of a man. So you can use a pictorial structure or you can use generalized cylindrical representation to identify the head, the torso, the arm, and the limbs. So this is called geometric primitives. These were one kind of representations that were used in the early 1980s. In 1980s and in 1920s, there were different representation in a different space. They used orthogonal polynomials like the moments and the edge descriptors. These help us derive the primal sketch, the primitive features like the edges, blobs, the corners. These help us to derive these parameters from the image and use them as descriptors to represent the information, the underlying information in the image. In 1999, there was one other major breakthrough called SIFT descriptor, the scale invariant feature transform, where they use basic edge detectors to find out prominent edge features. These edge features serve as the descriptors for this image. And when the same image is subject to any sort of transformation, it could be translation, it could be rotation, it could be scale, it could be perspective distortion. In this case, for this example, we are seeing the same image that's being rotated in a different direction. While for human eyes, it is easy for us to recognize whether the image is translated or rotated or shrinked to a different size. It's easy for us to recognize these both are the same images, but it doesn't work that way for the machines. For machines, you will have to give descriptors that uniquely identify these images irrespective of these transformations. So during this period of 90s to 2000 is when there were a lot of machine learning, a lot of work on machine learning techniques, and a lot of machine learning algorithms came up. 2001, Waller and Jones developed a system for face detection. So that is one of the first machine learning application where the machine, given an image, the machine can automatically detect human faces in the image. So while the research was progressing in this way in the computer vision and the image processing area, there was in parallel another stream, there was in parallel developments were happening in the field of artificial neural network. Even before we get into what artificial neural network is, let us try to understand what an artificial neuron is. In 1940, McCullough and Pitts proposed artificial neurons. So what did they say? You can this single node that you see here, consider it as a single cell, a single neuron in your brain. So they say you give any number of inputs to a neuron. So this neuron understands the data as a linear sum of the input data, and then it does the interpretation based on that. Say, for example, here you have a single neuron where you give inputs x and y. So the response or the stimuli that this neuron sees would be summation of some value, weight value here. I can call it as, say, W1 for now. And here I can call it as W2. So they say the response that this neuron would give, it'd be X into W1 plus Y into W2 and plus bias. So this way they were able to give a mathematical model for a neuron The weights that you see here, W1 and W2, are adjustable, but they are not learnable. So using this artificial neuron, they very well demonstrated the and, or, and not gate operations. However, with this artificial neuron as the basis, in 1957, Rosenwald, Woodrow, and Hoff proposed perceptron. So this perceptron, so like I said, artificial neurons that were proposed in 1940 were not learnable. In 1957, Rosenwald et al. Proposed a perceptron which we also call as a single layer or a single neuron artificial neural network. So the perceptron is modeled in such a way, the activation is again going to be the same. This is nothing but summation of I1 W1 plus I2 W2 plus I3 W3 plus I4 W4. It's going to be the same, but then these weights W1, W2, W3, W4 are learnable. So, and the output of this neuron after summation would be subject to activation function, which here we also call it as thresholding. So why do we do thresholding? If suppose all these 4 inputs are significant, if the combination of these 4 inputs are significant, then the neurons would respond. Say there is a dark pixel and there is a bright pixel. When you see them, see the dark pixel, you are able to recognize the dark pixel, you are able to recognize the white pixel, but you clearly don't know which part of the neuron fired in your brain whether it recognized the white pixel or it recognized the black pixel. So basically what this theory says is that if there are if these input values are significant, and if the summation of those values is above a certain threshold, means it's beyond a threshold that the perceptron or that the neuron can recognize, that is when this neuron gets fired, which means that is when this neuron responds. Otherwise, this neuron does not respond. That's the concept behind the perceptron. This was an interesting concept, and it very much was analogous to what Hubel in his experiment, in the cat experiment, concluded. They said not all neurons respond to all the stimulation. Each neuron responds to a different kind of stimulation. That's exactly what is being explained here as well, or established here as well. But later, in 1969, Minsky and Papert showed that the perceptron is very well suited for solving linear problems, but are not suitable for solving XR problems. In 1980, Kunihiko Fukushima proposed the first convolutional neural network, which is called as neocognitron. Let me not get into the details of what this convolutional neural network is, but then let me give you an idea of what it does. So what he did was, he took an input image, and then he borrowed the image processing techniques. He initially derived the image primitives like the edges, the corners, or whatever features that best describe, that best represent the image data, which we call as feature descriptors. And he used the feature descriptors in order to classify or identify what is the underlying pattern. But what was the limitation at that point of time? These weights were not learnable. We didn't have a technique for training or for automatically learning the weights. In 1986, the concept of multilayer perceptron was proposed. So the structure is the same. It basically tells the XR problem can be resolved if you have multiple neurons in the architecture. So they said you get the input and you have a layer called a hidden layer. There can be one or more hidden layers here, and each of this input can be represented as linear combination of one or the other inputs, and you add a bias as well. you add a bias to convert the linear relation to a nonlinear, to bring in the nonlinearity in the representation. So the output of this neuron is nothing but similar to what I said would be the output of an artificial neuron. The output of every single neuron here in the hidden layer and in the output layer is nothing but the summation of the weighted sum of its input plus the bias. Neural network is a supervised learning problem. So when you give a set of inputs, you clearly know what outputs you expect. So when you, given that you know the input and you know the output, initially you select a random set of weights and biases and you compute the response that you get at the outputs. You see the response that you get at the output is same as the actual output. If that is not the case, you compute the error and you use the error to update the weights and biases of the neurons in the hidden layers. So this is the basic principle behind multilayer perceptron, and this forms the fundamental architecture for any neural network that we see these days. With this concept of backpropagation and with the architecture, the CNN architecture, that was the neocognitron architecture proposed in 1980, LINET is a convolutional neural network architecture that was developed in 1998 for digit recognition. So basically see here, this is an input image. So here in the input image, you basically perform convolution to derive the feature descriptors of the input image, and then you sample it. Again, you perform convolution. It's basically like, you derive the features in the input image in a hierarchical manner. Your ultimate goal is to derive a set of features that uniquely represent only this data. That data is given as input to the neural network. In 2012, Alex et al. Proposed a convolutional neural network called AlexNet that had similar architecture like the LINET proposed in 1998, but with some more added advantages like data augmentation, like the network would be able to recognize objects in case of slide transformations as well. So in 2012, Alex et al. Proposed this AlexNet, and there is a competition called ImageNet Challenge that's been happening over years since 2008 or 2006. And if you see in 2010, AlexNet won the competition and the error rate was manifold less than what has been proposed so far in 2011. And this started to be the golden period for neural networks. Now, when people realized the power of combining the feature descriptors and the neural networks, then a lot of researchers started investing in the convolutional neural networks, and now, given a image data set that contains 1,000 classes, we are able to achieve classification with error rate as less as 3.57. Right. So like I said, convolutional neural networks completely change the way how the computer vision technology, it did not completely change the way, but it completely enhanced the way how computer vision technology delivered or offered solutions. So for us to understand this computer vision neural network, first we'll have to understand the feed-forward network. So feed-forward network is nothing but the multilayer perceptron that I explained few minutes before. So like I said, each neuron that you see here is an artificial neuron. So the output of this neuron is nothing but weighted sum of its inputs plus some thresholding. That is the output of each of this neuron. So in a feed-forward network, you have three types of layer: input layer, hidden layer, and then output layer. So input layer is nothing but the input values. Suppose, suppose you say, I have a grid that has a number 2. Let me consider it as a, maybe for simplicity, let me consider it as a 3 by 3 grid. And let us imagine this is a binary pattern. So I would say this is 0, 1, 0, 0, 1, 0. This is not accurate, but just to give you an idea, 1, 0. Now, if suppose this is the image pattern we have in our hand, you flatten this to a vector. So then your values would be 0, 1, 0, 0, 1, 0, 0, 1, 0. And this is what is your input. So this first value would be your x1, the second value will be your x2, the third value will be your x3, and so on. So these input data values comprise the input layer. These weights are randomly chosen, and then you can have as many hidden layers as you want, and the number of hidden layers you would need in your feed-forward network completely depends on the dimensionality of the data that you are dealing with. So what happens? So like I said, this H1 is an artificial neuron. The output of this H1 is weighted summation of its inputs plus some thresholding. In here, we also call it as an activation function. So why we basically do this is to introduce the nonlinearity. So same in the case of the second hidden layer. You can compute the output of this neurons using the expression shown here. Everything is the same except that the weight values are different depending on what weight connections it gets from its previous values. So here the information is progressing in this direction. So this is called forward pass. Now if you give some set of inputs, you already know what the response should be. For example, say I'm going to give an input 1, 0, 1. I know my output should be 1 here. If that is what I expect. The estimated value, y cap, the value that's estimated as a weighted sum of the response from these neurons in the hidden layer and these weights is y cap. So I compute the mean. Since here I'm showing only one sample, I just put it as y minus y cap. But if there are many samples, then this would be a mean squared error. You compute the mean squared error, and our goal is to derive these weights and biases in such a way that this error is equal to 0. So now when you compute your y cap, you find the difference between the computed value and the expected value, and you use that error information to update weight values in each of the layer. This is called backward pass. You use this, you find dou E by dou W, what's the difference in the weight with regard to difference in the error with regard, what should be the error with regard to weights in each of this layer. I'm not going to get into the mathematical details, but here to give you an idea. So what is the error with regard to this error? What should be, by what amount the weight value should be updated? So based on that, you update every single weights in the hidden layers and the biases in the hidden layers until you arrive at convergence, which means until this error is minimum. So this is the basic concept behind feed-forward network. And this network is the one that is being used as such in all convolutional neural networks that we see in these days. Okay, now that we understand there are layers, there are different nodes called neurons, and the response of the neuron is the weighted sum. It's kind of linear combination of the input. Why can't we just stop with flattening the image and giving it as input to the neural network, and then allow the neural network to train and give us the correct weights and the bias combinations? Why can't we directly use the feed-forward neural network for image classification? Basically, there are limitations. The first drawback or the limitation of using feed-forward neural network for image classification is the input, you will have to flatten the input data. It accepts only one-dimensional input. It doesn't accept two-dimensional input. So in case of images, the spatial correspondences are one important factor that help us understand the visual data. When you flatten the data, you basically ignore the spatial correlation of the image structures and you are losing information. And other disadvantages, sensitivity to translation. Say, for example, say I have a image here, I have a structure here. So if I write this, flatten this, suppose say this could be my maximum value 4, it could be any other value. I really don't care. So if I flatten this data, the vector would be, yeah, I don't care, I don't care, I don't care. I have the 4 here, and then the rest of the values. Now, the same data, I'm going to translate it spatially. Say, consider a new image where this value of 4 is here, and the rest is all, I don't care. So what would be the corresponding flattened vector? The corresponding flattened vector would be x, x, here this don't care, don't care, don't care, all this don't care, and then this would be 4. So you see how the vector has changed. So when these vector changes, the way how the weights are organized or the weights are assigned, the biases are assigned, also gets changed. The neural network no more recognizes these both as the same problem. Instead, it treats them as two different problems. That is why feed-forward neural networks cannot be directly used for image classification, because given an image, given a scene or given an image, wherever you have an object, if the object of interest can be present here, the object of interest can be present here, anywhere in the image, but then you want your machine to correctly recognize that this object is present in the image irrespective of where it is located, which is not achievable through feed-forward neural network. And the third factor is the computational complexity. Imagine for an image of size 28 cross 28, the number of nodes in the input layer is 784. Now consider what if you have a image of size, say 100 cross 100. The number of neurons and the number of weights increases exponentially with the size of the input image, that many computations. Hence, the solution is convolutional neural networks. Let us see how convolutional neural networks solve these problems of feed-forward neural network. So basically, every one of us know convolution is a process of transforming a data by applying filter over each entity and then compute the response with respect to its local neighbors. So what convolution basically does is it basically captures spatial relationship between neighboring pixels. Say, for example, f of xy is the image and w is a filter of size 3 cross 3. So what I do here is I take this filter, I slide across the entire region of this image, and I register the response, which is g of x comma y. There are two parameters that one have to remember when you do convolution. One parameter is padding, the other parameter is stride. What is padding? Suppose say, now this is your 2D array on which you want to perform convolution with this filter, with this 3x3 filter. So you will have to place this filter in such a way that it accommodates within this image itself. So when this filter is placed over here, it gives you the cumulative response with respect to this center pixel. However, this is the filter and this is the response. So when you place this filter over this region of the image, it gives you the cumulative response with respect to the center pixels, but what about this boundary pixels? The edge pixel, the boundary pixels of the image doesn't get represented, which also leads to, reduced, the size of the response image is also reduced. So without padding, the edges or the boundaries of the image are only partially processed. So, but then the boundaries also have crucial information. So in order to bring the boundary pixels into account, you add zeros artificially across the four corners. This process is called padding. How many zeros should be padded across the vertical and the horizontal dimension? That depends upon the size of the filter that you have chosen. And then what is stride? Like I said, you take a filter, you slide this filter across the pixels or across this 2D array and compute the response in each of this location. There are different ways. First, you keep the filter in this location, compute the value, and then you can go to this next immediate location, or you can skip this and go to the next immediate location. Skip one and go to other location. This is called stride. How many times you're jumping from the current window location? That is called stride. Okay, so here is an example that clearly explains what is stride by 1, stride by 2. Suppose here is the input data. These blue, red, green are nothing but the way this blue box, this 3x3 region is what is the sliding window region. So if it is stride 1, you come to the next location would be the next immediate column, and same way it would be next immediate row after this. If it is stride 2, you slip this, you slip one column here and then you go to the next column. So you jump 2 times, you skip 2 times. So depending on the stride you choose, the size of the output feature map would vary. We use this convolution operation in image processing to perform filtering operations such as blurring an image, sharpening an image, to perform edge detection and more. Here is an example, of convolution operation with these 3 filters. So here is a grayscale image, and these are all custom filters. I just put the kernel values on my own. So you can see here when you convolve this image with this first kernel, first filter, you can see the kind of features that are being highlighted. In the first filter, you can see the horizontally oriented features are highlighted well, the edge features are highlighted well. For the second filter, the circular regions, or I would say the diagonal features, are highlighted, and then for this third filter, the vertical features are highlighted. So this is what Hubel's experiment has also confirmed. Like our human visual system is neurons. Every single neuron is activated by a different stimuli. So now that if I could have this set of kernels that can help me to derive this primitives in the input image, I can use these primitives to act as feature descriptors for my image. That's the idea behind convolutional neural network. So these are all the important components of convolutional neural network. You have an input image, you have a kernel, which I call it as a filter. You do convolution, you convolve your image with a filter. And again, when I say I use kernels, not necessarily that I should use only one kernel. I can use as many filters as I can want. Say I can have one image here, and I can have 3 types of convolution filters. If the dimension of my image, for simplicity, I'm taking it as m cross n. If my dimension of my image is m cross n, Let us assume the stride value as 1 and padding as yes, then I can expect my output image to be of same size as the input image. Right. So now that I have one image, I want to derive the feature descriptors, which in neural networks we also call as feature maps or activation maps. So what happens when I have this M cross En image and I have a 3 cross 3 convolution filter, 3 number of 3 cross 3 convolution filters, then as a result of the convolution operation, I will have M cross N cross 3 feature maps. Again, like I said, we are just discussing about the components of convolutional neural network. Of a convolutional neural network, we haven't gone into how convolutional neural network is going to resolve the limitations that we saw in feed-forward neural networks. So likewise, I can have as many convolution layers as possible. So once you convolve the input image with these filters and you get the feature maps, then you perform an activation or a thresholding operation called ReLU activation. We will get into why we do ReLU later. So you convolve, you get the feature maps, you perform ReLU operation that makes your first convolution layer. After you convolve, you do pooling. Pooling is nothing but subsampling, or I would say downsampling. So this process of convolution, ReLU, and pooling, you can do as many times you want. So like I said, since pooling is a downsampling operation, suppose in this example, I have used 3 convolutional layers. At the end of this convolutional layer, I would have a set of feature map that will have lesser dimensionality than the input image. And this data will be flattened and fed as input to the feed-forward network. This feed-forward network will perform classification. Now, this is the architecture. And one other thing with the convolutional neural networks is, in the previous case, I've shown you an example of using, fixed kernel coefficients. But in convolutional neural networks, you can perform training in such a way that you don't only learn these weights in the neural network, but you also learn the kernel weights that you use for performing filtering. This is where we tell deep learning this is the major difference between machine learning and deep learning. If you could recall the slide where I showed the difference between machine learning and deep learning, I said in deep learning, you don't need to extract the features. The reason is this. You start at some point randomly, and then depending on the output response you get, you backpropagate the error, you adjust the weights, you adjust the kernel coefficients in such a way that you iteratively you arrive at the optimal kernel values and optimal weight values. So now this is the basic concept behind convolutional neural networks. In this initial phase, until you derive the feature map from the input image, this is called feature extraction process, and the process that's associated with the feed-forward neural network is called the classification process. Okay, if you could recall, I mentioned 3 limitations in the feed-forward neural network. The first thing, that it does not capture the spatial relationship in pixels. Now let us see how this spatial relationship in pixel is captured in convolutional neural network. Like I said, this is an input image. This red color, consider this red color as a separate box. It's a kernel. So I perform a convolution operation at this region. So I record in response. I record the response that I get for this pixel. Same way, and another example. Let me consider that I get the convolution response with respect to this pixel, and in the first pass, you see, I would have got the the filter response at this pixel region and at this pixel region. So this is the feature map that we get in the first convolution layer. Now, the second convolution layer, I use a different set of filters. This gray region, consider it as a separate kernel. Once again, I do a convolution operation here, but here this time, the response, the convolution response is calculated with respect to this pixel. Similarly, there is another kernel here. I put another kernel here where I capture the convolution response of this pixel. And in the second convolutional layer, again, I put a new filter. You consider this green box as a new filter. I perform one another convolution operation. This convolution operation is going to give me the response for this center pixel. Now, if you map it back, now this is your output feature map. If you see, if you take the value of this value that you get at this point in the feature map, it is not just explaining you the spatial relationship between the pixels in the layer before it, but then it maps back to a bigger region. In this local region that you considered for computing the response, you have two pixels that exploit or that contain the spatial relationship with regard to these two regions in the first convolutional layer. Likewise, these pixels here contain information about a different spatial region in the input image. So you see, it's basically, this is what we call it as local receptive fields. So it's basically this one single pixel is having information about this big region. So you can understand how the spatial relationship between the pixel or between the neighborhood pixel is being preserved across the different convolutional layers and is preserved in the output feature map. And then, so now that we addressed how the spatial relationship is being captured, now we need to find why do we need a ReLU operation here? What is the ReLU operation? So consider this as an input image. This is the first convolution layer. This is the second convolution layer. So each convolution operation, is a linear operator. When you stack one convolution, another convolution, you still get another convolution, which is a linear operation. So, which is basically when you go back to the perceptron neural network case, where it had the capability only to classify linear data points. So we need to, in order to insert the nonlinear capability, you need to insert a nonlinear activation function between these two convolution operations. So this ReLU is, you can either, you call it as an activation function or you see it as a thresholding operation, everything is the same. So ReLU is the rectified linear unit. So what it does, this is the activation function. This is the response graph for ReLU. So you have, say for example, now this is the activation map on which you are applying the ReLU operation. It basically sets all the negative values to 0 and preserves only the positive values. And then why pooling? So now we addressed the limitation of spatial relationship in feed-forward networks. We also understood how we bring in the nonlinearity in the convolutional neural networks. And next problem, big problem in hand, is to reduce the computations and make your convolutional neural network robust to translation variance. So what is this pooling? Pooling is basically a subsampling. It's a downsampling operation. How do we, there are two parameters in pooling. First, the kernel size, and the next one is the stride. What do you mean by stride? Suppose say this is the uh, feature map or the activation map in hand on which you will have to perform pooling. Let me consider a 2 by 2 filter, a kernel, where the coefficients of these kernels will be always 1. Remember, there are learnable parameters in convolutional layer, but there are no learnable parameters in the pooling layer. So you place this kernel over the image, and then there are two ways in which you can perform the downsampling operation. Either you find the maximum response in this filter region, or you can compute an average of the response values. So if you compute only the maximum values, it is called max pooling. When you compute only the average values, it's called average pooling. And what is stride? You can move this filter across this activation map in any steps you want. In this case, I say my stride is 2. So I put my filter, first time I put my filter here. If the stride is 1, then my immediate placement of my filter would be in this location. But then my choice of stride is 2. So I would leave away this location and I would put my filter in this location and compute the maximum value or the average value within this region. Likewise, the stride is not just applied in the horizontal direction, but also in the vertical direction. So you can see originally when you have a feature map of size 4,4, and when you apply stride operation, when you do pooling, the feature map size is reduced by 2,2. Now this is the amount of or the computation savings that we get in convolutional neural network. So now, should we be worrying about losing spatial information? Absolutely no, because convolution operation itself preserves the spatial relationships between the pixels. So when you take every single one pixel in the output feature map, then it would obviously be a combination of feature descriptors that are present over a wide region or that are present over a wide neighborhood in the input image. And above that, when you perform ReLU operation, you ignore the non-significant the non-significant feature descriptor values, and you take only those feature descriptors that are dominant. And then as you perform the pooling operation, we don't ignore values. Instead, we either select dominant values or we either find an average of it. So that way, the information, you can consider it as from one convolutional layer to other convolutional layer, it is compressed and it gets accumulated over from one layer to the another layer. And now, how do we achieve translation variation? Like I said, convolutional neural network capture the spatial relationship, capture the important points. Suppose say you have an image here that has a maximum response, or that has a object here that would give me maximum response. When I do max pooling, let us assume here it's going to give me maximum response at this point in the after pooling. The same image, if the object is misplaced in a different location, say in a different location, the response that the feature map would get for this would remain the same because the weights are symmetrical. You apply the same weights across the entire image. So wherever this object is placed in the image, the feature map response is going to remain the same. That is number one. And number two, even when you perform ReLU or pooling, this pixel would be located in a different place, but it will not be ignored, or it won't become insignificant. So that way, even if the object is being translated or put in a different location, we do get information, the same information about the object. So this is how we achieve translation variance in convolutional neural networks. Now this is how the final connected layer of a convolutional neural network that you can use for image classification looks like. You have an input, convolutional plus ReLU layer. It does convolution, derives the feature vectors, and performs the nonlinear activation. It reduces the dimensionality, and you keep going, and then you have a final feature map which has much reduced dimensionality than your input image. And it's given as input to this is nothing but the feed-forward network. In addition to the actual feed-forward network, we have a layer called softmax layer. What does the softmax layer do? Your feed-forward network actually gives some scores, some values for each of the object that it identifies. The softmax layer converts these values into probabilities. So when you put a softmax layer, you will know, okay, if this first the first node is for object class car, whatever be the input image, it would say, hey, this has a probability of probability of object being car is 0.9 likewise. Let me show you a quick demo. Give me a minute. So I'm going to show you demo of AlexNet, which is a convolutional neural network, and the architecture of that convolutional neural network is very much same as what we have discussed so far. So one major advantage in convolutional neural networks is you train a network on a data set, you have the network ready, and then you can reuse that network any number of times to detect any similar object classes. So this, like I said, this AlexNet is a convolutional neural network that is trained on a data set that contains 1,000 classes. So this has information about what all different classes on which the AlexNet is trained. So what I'm going to do is, in MATLAB, we have a trained AlexNet. So if you just call net is equal to AlexNet, it is going to load the trained network for you. I have already put together a MATLAB code here. So let me show you here first. I'm going to load the AlexNet. So you can look at how this network looks like by using a function called analyze network. That's going to show you how many convolution layers are there, and yeah, this is the network architecture. So it says first convolution layer, ReLU layer, and then a normalization layer. Normalization layer is actually why do we perform normalization? We perform normalization to ensure that in every layer the distribution is like of the data is zero mean and single variance. Only then the network would train and you will be able to arrive at a convergence. It's basically because from one layer to the other layer, you keep stacking, accumulating the values. It's very likely the mean of the distribution and the variance of the distribution would change, and that is indirectly going to affect your convergence or your training results. That's why we do normalization. So now this is your convolution, ReLU, normalization. This is your first convolutional layer, and then you do pooling. Then you have a second set of convolutional layer, third set of, likewise, you have 5 convolutional layers in this AlexNet, and then this FC is nothing but your feed-forward network. So you have 3 fully connected layers, and then you have the output layer. This prob is nothing but the softmax layer that gives you the probability. The output layer is the one that displays the output. So this is how this is the network, like visualization of the AlexNet network architecture that we're going to see now. So one thing in convolutional neural network is the test image that you want to classify should be of same size as the training images. If suppose you used the images that you used for training your images is training your network is 100 by 100, then your test images must also be of size 100 by 100, which you can achieve by simply resizing the image. So that is what I do here. So I know that image, AlexNet, the ImageNet has classes to classify wine bottles. So I just read an image randomly. I downloaded a random image from the web, and I run this, image classification. Then I see this is the test image, and it tells the label, oh, this is red wine. Now, we can simply select any other thing, say for example, violin. I see violin, let me download any violin image online and then see if our AlexNet can recognize the violin image. Going to yeah. So likewise, you can use the already pre-trained AlexNet to apply for any of the image classification problems that you have. So what we have seen right now, until now, is the image classification problem, but there is one other problem in computer vision, which is deduction. So what we did so far with the convolutional neural network is you give an image and then you tell whether the image is X or Y. But the object detection problem is even more bigger. So where you give a test image, we not just want our network to tell what is this image, but we want our network to locate the image. So when you identify the image, and when you identify an object in the image, and when you also locate the object in the image, then it is called object detection. So object detection, for object detection, you don't need new neural network architecture. You can reuse the same convolutional neural networks with little modification. So what I can do here is, now that I know, so I hope you understand this is nothing but a convolutional neural network. I just put its component here, convolutional layer pooling, feature maps, and then give it to a fully connected network. I just put it likewise. So if you have a test image, now I want my convolutional neural network not just to classify, but also to tell me where it is. So what I can do is I can use a sliding window approach. So before giving my test image as input to the CNN, rather than giving the whole image as input, I would probably select portions of these images, give it this as input to the CNN, and see where it returns. So since it is me, I'm going to use a sliding window approach here, and my window can be of any number of, I can have any number of windows, and the size of the windows can be any, which is basically multiple scales. So since I select the regions, I clearly know the coordinates of the regions that I select and I give as input to CNN for classification. So that way I have the coordinate information. I store the coordinate information while selecting the regions, and then I see what is present in that. If say for example this region has an object, then my network would say yes object or no object. If it says no object, then I ignore. So likewise, if I keep going, when I give this window, this region of the image, test image is fed to my convolutional neural network, it's going to tell me, yes, there is a dog. And then I give another region, a small region, this region also contains the dog. So my convolutional neural network would still tell there is a dog. So if you see at the end, for such approach, I will not get just one bounding boxes, but then I would get multiple bounding boxes since I'm using sliding windows of different scales. So whenever any region within which the object is present, it's going to give me there's an object here. But then how do that means what I get multiple bounding boxes for one object. How do I resolve this problem? I resolve this problem using a technique called non-maximum suppression. So what is non-maximum suppression? So whenever an object is classified, you remember that a probability score is assigned. So I see what is the probability. Suppose say the first time I give this region, I get a probability score. I know the bounding box values. The second time I get this, and the third time I get this. So for every bounding box location where the network detects an object, I get the probability values. Among these probability values, I see when I get higher probability value. So the bounding box for which the classification score is high, I would retain that bounding box and I would ignore the rest of the bounding box. This way, I solve the multiple bounding box problems in detection. Again, is this a very efficient method? Definitely no, because the number of windows that you should choose is large. And again, will the bounding boxes that you get at the direction output be a correct fit? No, because it completely network does not have any control over the bounding boxes. It completely depends on what you specify at the input. So we would either end up by loosely putting a bounding box over an image, or yeah, majorly by loosely putting a bounding box over an image. It would not be a tight fit. So that is when we decided to automate, or we decided to teach the convolutional neural network to learn the bounding boxes the same way how it learned the image features. So this approach, this is again CNN, but the approach that we follow to um, estimate the bounding box coordinates is called as bounding box regression. So give an image, convolution and pooling is the same. You get the feature map. Until then, everything is the same, but instead you will have two fully connected layers. The first set of connected layers is to classify the object, and the second set of connected layers is to determine the bounding box coordinates. So what is the difference here? Previously, for image classification problem, you just had to specify the input and the class name, but for an object direction problem, you specify the input, you specify the class name, and also you specify the bounding box coordinates. Now, since your feedforward network already knows what should be the bounding box coordinate for the given input, it would train the network in such a way that the weights and bias values are adjusted such that the predicted bounding box coordinates match with the actual bounding boxes. This is what is called regression, bounding box regression. We call the first stage feedforward network that classifies the object as the classification head, and the one that determines the bounding box as the regression head. So this is what happens in regression training. So in regression training, we use simple L2 laws, L2 norm laws. So what we basically do, you already know what should be the expected bounding box. You give the bounding box coordinate as input to the network, and then you train the network until the difference between the actual bounding box coordinate and the predicted bounding box coordinate is minimum. So this is another stage of training in object detection. So I hope this has given a brief overview, definitely not an in-depth knowledge, but a pretty decent overview of what is image classification, what is object detection. But these are all very fundamental techniques. So these days, there are even more advanced methods in object detection. Like if you see the current approach that I said, the regression approach or the sliding window approach, they are still computationally expensive. And when you process the image, now this is the image region. I know this is, I want to find a bounding box with regard to this region alone, but then I'll have to evaluate the rest of these regions also. So there is so much of computational wastage here. So there are several advanced techniques like region-based convolutional neural networks, you only look once, YOLO CNNs that overcome this problem and provide us more computationally efficient solutions for object detection and computer vision. So that's it. I've come to the end of this presentation. Thank you for patiently listening.
Yeah, thank you, madam, for such a nice talk. There are questions in the chat box. Let me go to the first question.
Okay.
The question is from Sri Lakshmi Prasanna. The question is, which simulator is used to simulate convolutional image?
What I don't understand. What do you mean by simulate the convolution image? Can you please explain that a little?
Sri Lakshmi, if you are there in the meeting, you can unmute and directly ask. The question is not clear. I think she might be asking about like any toolbox in MATLAB or that is required for this kind of simulation regarding convolutional images.
Okay.
Simulator
so
is MATLAB definitely, but what kind of additional packages are required? Perhaps that is the question.
Okay, so basically you just need computer vision toolbox and deep learning toolbox, primarily the deep learning toolbox. As far as the image is concerned, we don't simulate an image. If you have a camera, you might have your own images, or you can download any images online. It's basically the input images that we use are something that we capture, for the specific problem in hand.
Yes, thank you. There is one question from Dr. Savita Bhosale. The question is, which deep learning framework is suitable for computer vision?
Convolutional neural networks, definitely. And especially for object detection and image classification problem, convolutional neural networks are the best.
Yes, thank you. There is two questions from Pramod Kumar. Let me read out the first question. The first question is how to eliminate noise in the convolutional image processing technique.
Noise, see, the convolution operation itself will suppress noise. If you remember filtering operations, like I said, the example that I have shown you high-pass filters. Let me share with you my screen again to kind of bring back that slide. Just a minute, let me bring you back to that slide. Okay. Okay, if you see here, these are basically, I would say this has high-pass filters, right? Because if you see the response functions of these filters, it would be something like, zero crossings would be there. If I use a filter, say if I use a filter that is all positive values, it is basically doing a filtering operation. Say for example, if I use a filter like this, all positive values, even here, if it is all positive values, what happens if there is a noisy pixel, if there is noise anywhere in these images, since this is all positive values, it's going to perform an averaging operation. So that way it's going to nullify the noise. Whereas if you use high-pass filters, obviously it's going to highlight this noise. But you should remember, our convolution filters is not just about one filter. It's a series of filters. And it is not only high-pass filter. It can be low-pass filters as well. The values that, the kernel values are automatically or automatically chosen by the network in such a way that it reduces the output error. So when your kernel coefficients are all positives, then the noise will be automatically taken care of. Again, there is a limitation. What if this image is completely noisy? Then I really can't give you a figure of, okay, until 5% of noise it would work, until 10% of noise it would work. But I can tell that convolution neural network themselves are tolerant to noise to a certain extent. But if the noise is in such a way that it completely modifies or modifies the feature descriptors where you cannot derive the features, convolutional neural networks is going to fail. Did that answer the question?
Yes, thank you. I think you have answered that question. Let me go to the second question of Pramod Kumar. What is the use of the soft layer in the output side of the given diagram? So,
The
madam, are you able
softmax
to?
layer? I can hear you.
Yeah, I mean, that diagram, I don't know which diagram he is referring to. What is the use of the soft layer in the output side in the given diagram?
This softmax layer is what I think is. I guess he's talking about
ma'am,
this.
this one only.
Yes, please unmute and please proceed. Yes, Pramod.
Yes, sir. In this diagram only, what is the use of this softmax layer? And
right, sure.
that is, we call it as a output layer, na?
Right. Yeah, I'll tell you. So there is.
And ma'am, one more point. Just now we discussed the noise reduction. So why are you using the Gaussian filters in that images, ma'am? So many block diagrams I've seen.
In where did I? Are you talking about this filters?
Yes, ma'am. Gaussian filters. So many papers I've seen Gaussian filters to remove the noise in that convolution images.
Okay. You primarily want to know why they are using Gaussian filters alone to remove noise, right?
Yes, ma'am.
Because,
Yes, ma'am.
Because I think because it's how naturally the image distribution is similar to Gaussian distribution. That's how you model the images. See, when you perform a denoising operation, what you're basically doing is, if you know what is your what's the distribution, how your data is distributed, then predicting the true value becomes easier, isn't it? So we believe all natural signals follow Gaussian distribution. So if you plot the pixel values in the image, we believe that the distribution follows a nice Gaussian distribution. So any value that is corresponding to the image should fit that curve. If it is an outlier, it will not fit the curve. Then this averaging operation will help us bring that outlier close to the actual bell-shaped curve. It's basically because we believe all natural signals follow the have the Gaussian distribution. That is why. Did that answer your question?
Yes, ma'am. And what is the necessity of that softmax layer, ma'am, in the output side?
Yeah, softmax layer, if you see the fully connected neural network, the feed-forward network, the output of the feed-forward network would be some values, say 0.1, 0.3, it would be any values. But you have, in this case, suppose you say I have these classes, car, truck, van, and bicycle. I cannot just tell, for this first output node, I'm getting a value. One time you might get a value of 0.9 or 0.8. Some other time you can get a value of 1.5 or 1.8. How are you going to draw a threshold there to tell, hey, you get this value, then it means it's a car. You get this value, then it means it's a truck. How would you threshold it? Because the depending on the kind of input that you give, depending on the weight values, the scores, the values that you get at the output of the feed-forward network is going to change, right? So we want to normalize it. What is the best way for us to normalize it? If I could have a output that is going to tell me, okay, at this node, you rather than giving me a score and then letting me put a threshold there to tell when that is I should consider as a valid score, or when I should not, when I should ignore it. Instead, I put a softmax layer that will pick the values here and convert them into probabilities. So in neural networks, it is not always hit or miss. It is like you give an image, I tell the probability that the input is a car is 0.95, the probability that input is a truck is 0.1, the probability that input is a van is 0.0, likewise. So basically, for more confident prediction, the softmax layer helps us to convert the raw scores that we get in the get from the feed-forward network to probability values that will assign confidence to each of the object classes that we consider in this problem. Is that clear, Pramod?
Yeah, yes. Thank you, ma'am.
Thank you.
And will you calculate classify the analog and digital signals in the automatic modulation classifications, ma'am?
I'm not a comms person. I'm really sorry. I don't think I'll be able to answer this question.
Yeah, okay. Thank you.
Okay.
Yeah, thank you for the question and thank you, madam, for answer. There is one more question again regarding communication. So from Vijay Selvan, the question is, please give some idea about CNN using in wireless signal classification.
Okay. Yeah, I know convolutional neural networks are used in 1D signals, like in speech signals, but in case wireless signal classification, I can say that works are there. Like you can see a lot of. Recently, I read some review papers. This is absolutely new area for me, given that I'm not a comms person as well. But there's definitely one item that I'm considering to kind of read about more, because since there will be more investments in this zone, what you can do, but I can tell you how you can use the convolutional neural network. So far what I have explained with regard to convolutional neural network, I have explained you in terms of 2 dimension. If you could reimagine the entire concepts by considering it as 1-dimensional, the same architecture, the same CNN architecture would apply for wireless signal applications as well. I don't think there should be separate tweaking on the network side except for the dimensionality. This might not be the perfect answer, but I'm trying to directly correlate with the problem in hand.
Yes, thank you, ma'am. I think there are no further questions. Participants, if you have any questions, you can drop the question in the chat box. Or otherwise, I guess there are no questions from the audience. So, madam, thanks a lot for for such a nice presentation. And it got delayed due to the previous session's question and answer. Sorry about that again. So,
no problem.
Yeah, I would like to thank you again and see you soon. Yeah, thank you.
Thank you very much. Thank you everyone for listening. Hope the session was helpful. Thank you.